Hello again. In this video, we're going to finish off chapter 1.1 by looking at some past paper questions, which include the ideas from this chapter. Here are the timestamps if you're looking for a specific question. If not, let's crack on with question 1. Question 1 is similar to one of the examples in the examples video. We've got a small ball and it's released from rest. It falls down to the ground and it rebounds upwards. And we've got to find the speed of the ball after it hits the ground, given that its impulse received from the ground is 4.2 Newton seconds. So, as usual, I'm going to draw a diagram. Here's our small ball. Its mass is 0.3 kilograms. It's released from rest, so it's going to fall downwards. And the distance it's going to fall is 3.6 meters. And it's above a horizontal ground, so I'm going to draw the ground flat like this. So what's going to happen? Well, it's going to get dropped, and some moment later, so I'll draw a secondary diagram at the side, it's going to hit the ground. So at some time later, it's going to be on the ground, and then some further time after that, it's going to have bounced up a bit. So it falls down and then bounces up. I'm also going to add the impulse into the diagram. That's going to be upwards, and it's going to be 4.2 as given in the question. A particle falling from a certain distance is definitely making me think of suvat, so I'm going to set out my suvat so we can find the speed of the particle when it hits the ground. The distance is 3.6, but I'm going to put minus 3.6 here because I'm going to define upwards as positive. U is 0 because it's dropped from rest. V is what we're looking for, so this is going to be a question mark. And A, as always, is going to be minus 9.8. Minus because gravity is bringing us down. So the suvat equation that I'm going to use is v squared equals u squared plus 2as. And once I put in the values, it's going to be u squared is nothing. And I'm going to do 2 times 3.6 times 9.8, or vice versa if you'd prefer. So if I calculate this, then v squared is going to be 70.56. So if we want v, we can take the square root, which is 8.4. So that means when this ball is being dropped, just before it hits the ground, its speed is 8.4. And we're interested in what's its speed right after. Now I've called it v. That's a different v. That's maybe a poor choice of letter. We should know the formula for impulse, which is m times by v minus u, where v is the end velocity and u the start velocity. I'm going to define upwards as positive, then the impulse is in the same direction. The mass is 0.3, and the end speed is v. The start speed, unlike v, is in the opposite direction to positive, so we have to do minus 8.4. Because v is in the same direction as the positive arrow, then we don't need any negatives there. This will turn into v plus 8.4. We can then divide by 0.3 on both sides. That should be the same as 42 divided by 3, so 14. And then we can subtract 8.4 from both sides, which should give our final answer 5.6 meters per second. Alrighty then, on to question 2. This question is worth 2 marks, but there were more parts after part A. We've got 2 particles, P and Q. I'm going to write their masses in the middle, m and 4m. So according to the question, they are initially at rest on a horizontal surface, and particle P is given an impulse. So it's given a little push. And it moves over and it heads towards particle Q. And at some time later on, the two particles meet. The masses haven't changed. But particle P moves in, hits particle Q, they collide, and then afterwards, from the question, it says that P is at rest and Q has speed W. So that means that P has not moved after the collision, but Q is on its merry way. This impulse it's received is called I, and the speed afterwards for Q is W. We're going to use the same formula as before. So we're going to need the start speed, which for Q is 0 because it starts from rest. I'm going to set up the equation for impulse for Q. As before, impulse is the mass times by the end velocity, so the velocity afterwards, minus the start velocity. Writing it in this way may be clearer when we have to use U's and V's in the formula as well as in the question. The mass of Q is 4m, so I'm going to write that here. The end velocity is going to be W, and I've not decided on which way is positive, but I'm going to make it towards the right. I'm going to make it towards the right because the impulse for Q would also be positive towards the right. The start velocity is 0. That doesn't matter if it's positive or negative, it's still 0. And this would finish off our 2 marks, times these two together. The impulse will be 4mw. Normally, if I was doing a question like this, I'd be using the conservation of linear momentum. Because I've only covered the content from chapter 1.1, I'm going to be using the impulse momentum principle instead. Essentially, it equates to the same thing, but it can make the working out slightly easier in some places. So for this question, if you know conservation of momentum, feel free to use it. If not, I'll show you the method that you can do. So we've got lots of information here. I'm going to write it all down in the diagram. We've got particles A and B. They've got masses 2m and 3m, and they are moving directly towards each other. So they're going to head towards each other, hit, and then bounce away again. We're told that the speed at the start, so before, for A is 2u, so I'm going to put that here. And we're told that the speed for B is u, so I'm going to put that here. That's before. Let's consider afterwards. The masses haven't changed, so I'm going to write 2m and 3m. We're given the speeds for A, which is 0.5u, and B, which is w. And you'll notice in the next sentence it says that the direction of each particle is reversed. So the arrow for A is going to the left and the arrow for B is going to the right. So the way I'm going to do this question is actually going to get the answer to part C first. But as I say, if you know the conservation of momentum, you're going to get part A first. I'm going to consider particle A, just like before. Impulse is mass times by the end velocity subtract the start velocity. The mass of A is 2m. The end velocity, well, I have to consider which way is positive. I'm going to get positive to the right as usual. So this 0.5u is the wrong way around. So the end velocity will be minus 0.5u. The start velocity is in the same direction, so it's going to be minus 2u, like this. If I simplify this, it will be 2m times by minus 2.5u, which will be minus 5mu. This means that the magnitude of the impulse is going to be 5mu. And this should make sense because the impulse acting on A is acting towards the left. It's hitting A and it's making it move backwards towards the left. Okay, we've done part C. Let's now do part A. So we're going to do part A by considering the impulse for B and then using this impulse momentum principle. So the mass of B is 3m. What's the end velocity of B? It's W. And it's positive because it's in the same direction. What's the start velocity? It's U, but it's in the opposite direction, so it's going to be a double minus here. So this means that the impulse is going to be 3m times by W plus U. The impulse momentum principle tells us that these two impulses that we've just found for A and for B should be exactly the same. So this should be equal to 5mu. So we can cross, get rid of the m's here, divide by 3 on both sides, and then subtract u from both sides to find that w is 2/3 u. That's the final answer. This is the only A2 question so far that uses just knowledge from chapter 1.1. So you might think it's harder, but it uses exactly the same ideas. We've got particles A and B. We've got masses 3m and m. They're moving towards each other, kind of like in question 3. Before the collision, the speed is ku for A, and before the collision, the speed is u for B, like this. That's before. Let's consider afterwards. So afterwards, the masses are still the same, but this time the speed is v for A, and the speed is 2v for B. You have to really be on your A game here because it doesn't say if it's towards the left or the right. It's a speed, so there's no direction given. The one thing we do know is that 2v is definitely going to the right. That's because it doesn't make sense for B to be going quicker than the A particle going to the left. So if the A particle is only v, B cannot be behind it going twice as quick. But A could be going left, or it could be going right. And once we get to part B, you'll actually see that makes sense because there are two values for k that we have to find. As in the last question, I'm going to consider some impulses. We're given that the impulse is 3/2mu. So if I consider the particle B, well, the mass is going to be m. So we can write that in the formula. The end velocity will be 2v. And I haven't drawn my arrow, but I always assume it to be positive going towards the right. And the start velocity, well, it's the opposite of what the arrow says. So the start velocity will be minus u. This is going to be equal to m 2v plus u. And the impulse is given in the question, so we know this is 3/2mu. And it's positive because the particle is hitting B, pushing it to the right. Here we can swoosh swoosh, get rid of the m's. And I'll times by 2. Subtract 2u. And then divide by 4 to give us the answer. So v is equal to u/4. Part B is the harder part. Uses the same idea as before. You can use conservation of momentum, but you can also use the impulse momentum principle. By considering the momentum for A, well, the mass of A is 3m, and we need the start and end velocity. If we go back up to the diagram, we don't know the end velocity because we don't know whether it's positive or negative. And that's where the two values of k are going to come in. So let's pretend that v is going towards the right. Therefore, it's going to be in the same direction. And the start speed is there is ku, and it's still in the same direction as positive. So end velocity minus start velocity will be v minus ku. Or maybe there's a different situation. Maybe v is going towards the left, in which case we'd have to flip the sign like this. So in the diagram, maybe it's going towards the left, which is the opposite of the positive direction. The starting velocity is still the same. That's not going to change. So we've got the two different cases. Now we need to quickly think about the impulse. When A is being hit, it's being hit with an impulse from B, and B is moving to the left. But I define positive as to the right. So instead of this being 3 over 2 mu, it has to be negative. Then the same is true for the other case. So we can now ignore this in the middle. We've now got two equations to solve. I'll solve the one on the left first. I'm going to get rid of the m's. I'm going to get rid of the 3's. So minus a half u will be v minus ku. I'm going to times everything by 2. And now I'm going to use the definition of v. So v was equal to u over 4 from up here. So this will be u over 2. I can then add this to both sides and add u to both sides. I can then swish, cancel the u's, and then divide by 2. This gives one value of k, 3 over 4. For the other equation, the same kind of deal. I'll cancel the negatives. I'll cancel the m's. I'll cancel the 3's. I'll substitute v, which is u over 4. I'll subtract u over 4 from both sides to get ku is u over 4. So half u minus a quarter u is still a quarter u. Cancel down the u's, and we get the other value of k, which is 1/4. How did you find these questions?